Okay, so all right. So like I said, so we'll I'll make all these talks available. I've been taught by my 10-year-old how to compress them and put them on YouTube. So I'll put links on our webpage, which I don't know if you've noticed the webpage, but it's getting fancier. It's got my picture. It's got a nice little header with some cool stuff. It took me forever to figure out how to do that, but oh, it is going to be there. I'm going to put some GIFs in there. We're going to go full. Like I said, I'm learning how to do forms now. So forms, anytime you click on anything, you're going to have to fill out a form. All right. All right, but seriously, so last week we spent a lot of time talking about classical fields, and we've gotten it to the point now where we want to start quantizing things. Okay, and it turns out that that's going to be our goal over the next, I don't know, a couple weeks, really, is quantizing a quantum field theory, or quantizing a field theory, right? And we're going to focus on, just for simplicity's sake, we're going to focus on the case of a real Klein-Gordon field. Okay, so we're going to start from that Lagrangian that we wrote down last time for Klein-Gordon field, and we're going to quantize it. Okay, and it turns out that there's several different ways that you can, quantize a theory, a field theory. One is called canonical quantization, which is based on the simple harmonic oscillator and what we did when we talked about second quantization. Okay, so that's what canonical quantization is. That's what we'll do today and maybe next time. The other way is the path integral formalism. Okay, and that's what we're going to spend the bulk of our time doing. That. Okay, it's going to involve a lot of confusing and new concepts in the beginning, but as you'll see as we get into it, especially when we start to talk about interacting fields, the path integral formalism is a lot better. It's a lot more intuitive. Okay, so canonical, if you look in Peskin and Schroeder, he jumps right in and does just canonical, and so there's a lot of confusion about how are these fields interacting? How do you write down terms and then get interaction terms out of it? And so I've come to love this path integral formalism, even though it's not what I was brought up on. I was brought up on the Peskin way. Okay. All right, and this is again another quick reminder that for the remainder of this class and the remainder of your life, we're working in God-given units. Okay, so we're working in units where h bar c, the Boltzmann constant, Newton's constant, whatever constant you can think of, it's 1. Okay, so I don't want to hear mention of any h bar or speed of light or anything like that, because you will immediately be expelled from class. If where? Even if I, oh no, here I misspelled here. So if I hear mention, not if I hear mention. It's if I hear you mention. You know what? I noticed that when I was reading it. I forgot to change it. Okay. Like I said, 8 and 10-year-olds. Okay. Just keep that in mind. All right. Okay. So the path that we're going to follow, well, that's a bad choice of words. So we're not going to follow path integral formalism right now. The path to quantization that we're going to follow right now is canonical quantization. And this is the type of quantization that we're used to, okay? So just like in normal quantum mechanics, the first thing you do when you encounter a system is you write down the classical Hamiltonian, right? You write down the classical Hamiltonian in terms of momentum and position, right? Or angular momentum or whatever, right? And then you reinterpret all the dynamical variables like position and momentum and angular momentum in terms of operators, right? So that's what we do. Write down the Hamiltonian, you promote variables to operators, right? And then the act of actual quantization comes in when you impose the appropriate commutation relations, right? So for the case of position and momentum, you impose, the canonical commutation relations that we've got written there in equation 2, right? So it works the same way, right? Last week we spent all of last week coming up with a classical theory for fields, right? We got to the point where we could write down a Hamiltonian for a field theory, right? And we do the same thing, right? We take dynamical variables. This time they're fields, right? So they're the position and momentum fields, right? And we promote those guys to operators, right? Big difference is now the fields and the momentum, the conjugate momentum of those fields are functions of not only time but the position variable, right? Now position is not a dynamical variable. It's kind of just a constant. It's not a constant, but it's a what's the word I'm looking for? So what? Parameter, right? It's just a parameter, okay? So we promote those fields to operators, right? And then we impose the appropriate commutation relations. Right? So in other words, we'll just impose, we'll just by analogy impose commutation relations between the fields, between the momentum fields, and then between the field and the momentum, we impose something that looks a lot like what we had before, right? But now we're dealing with continuous systems, so our delta function in general is going to be a three-dimensional delta function in the position parameters. Okay? And so just a point of note is that in these guys, these commutation relations are always taken to be at the same time. Okay? So the time I've just neglected to write down the parameter. Okay? But it's always understood that when you take a commutation relation and you don't see a time parameter, that you're taking it at the same time. Okay? Okay, so let's kick it off by talking about the Klein-Gordon theory. All right, so last week we derived the Hamiltonian for a classical field, for a classical Klein-Gordon field, and we got something that looks like equation 5, right? And we said this is, everything you can write down, that's second order in the fields, right? So the first term is kind of like our kinetic term for the field. The second term is what? Anybody remember? The shear, right? It's from deforming the field, any energy that you put into deforming the field. And then the last term is just kind of the rest mass term, right? It's the energy of the field just being there, right? Because we've incorporated special relativity in the way that we derived this Hamiltonian, okay? So in this function, the Hamiltonian, we've promoted phi, the field, and pi, its conjugate momentum, to operators, and that means that the Hamiltonian is obviously an operator, okay? And we can work out the equations of motion. We did that last time for the Klein-Gordon, and it just turns out to be, like a wave equation, right? Okay, so a lot of times we're going to see that, when we start with a Hamiltonian or you start with a Lagrangian, it's going to be a lot easier to work in momentum space, right? Because the reason is that we're always going to want to work with Fourier modes, right? We're going to work with Fourier transforms of the position space fields, and that's going to help us because if we work in momentum space by doing these Fourier transforms, we've got these derivatives, right? And these derivatives, we can, in positions in momentum space, we can replace them with the momentum operator, right? So it's just going to give us factors of the momentum squared back, okay? Well, let's see how this works, okay? So let's start with the equation of motion, right? And for that equation of motion, I'm going to replace the field in terms of its Fourier transform, okay? So we're doing a Fourier transform in the 3 spatial dimensions. Later on, we'll do the transform in 4 dimensions, space-time. But for now, let's just keep it to 3, okay? And we know that we want phi to be real, right? That's just by saying that we want to work with a real Klein-Gordon field. And so that means that phi star has to be equal to phi, right? It's a real field, so phi star equals phi. So if I take the star of this guy, these guys are real, so this becomes minus, right? So to get the field back, I have to take p to minus p, right? Because then that'll give me another minus sign makes that a plus, and then I'll get phi star equals phi, okay? So just keep that in mind. All right, so I plug in my Fourier transform, right? And now I can take these derivatives, right? And they just pull out factors of, like I was saying, the momentum squared, okay? So this is telling us that the stuff in curly brackets, because the other stuff is just integral stuff, that the equation of motion in momentum space is what we would have gotten if we would have just replaced our normal minus I del with a P, right? Just a normal relationship in quantum mechanics between spatial derivative and the momentum, the linear momentum, all right? So this looks a lot like what? An equation of motion for a harmonic oscillator, right? If I replace that p squared plus m squared with omega squared, you're going to tell me that's a simple harmonic oscillator, right? So it's telling me that I'm starting with the Klein-Gordon equation of motion, right? I do a Fourier transform, and I get something back that looks like an equation of motion for a harmonic oscillator, even though phi here is not a wave function, it's a field, right? So there's a difference, but it's telling us that maybe we can use all that crap that we learned in quantum mechanics 1, you know, about how to quantize a simple harmonic oscillator. Maybe we can use it to quantize this this quantum field, right? This quantum field theory. Okay, so that's what we're going to do. That's what canonical quantization means. Is that we're going to use our, you know, the tools that we learned back in quantum 1. Okay, so to do that, before we jump right into it, it's a good thing to always review how we quantize the simple harmonic oscillator. Okay, so let's do it in one dimension. All right, so we have something that looks like that in equation 12. We have the harmonic oscillator Hamiltonian, got the kinetic term. I'm just setting m to 1 here, okay, the mass. And we've got the potential term, right? And the way you can do this is you can go off and you can use Hermite polynomials and all that BS, right? But we don't do that. We use what's called the factorization method, right? Where you write down annihilation and creation or lowering and raising operators, right? And you're able to factorize the Hamiltonian, right? And when you do that, so you factorize it by defining A and A dagger. You can invert those to write Q and P in terms of A and A dagger, right? And then your canonical commutation relations between the position and the momentum become canonical commutation relations between A and A dagger, okay? So you replace Q and P with A and A dagger. And when you do that, the Hamiltonian factorizes into this nice compact form, right? Where we have something that has units of energy, because remember, we've set that thing that I can't say, we've set it to 1, okay? So this now has units of energy. All right, so the Hamiltonian goes like this, right? And we define that AA dagger to be what we call a number operator, okay? So this is what our Hamiltonian looks like after we do some algebra, right? And so we ask, okay, what are the states? Okay, how do we define the states? And we actually build the states by hand, right? So we start off with a state that has, you know, that is the ground state, right? And we denote that by a 0, okay? Right, a 0 inside of a ket. Right, and we say, okay, let's define our formalism such that this A, when it hits the 0 ket, the vacuum ket, it destroys it, gives it 0, okay? And from there, we're able to build up our states, right? But one of the kind of interesting consequences of this is that if I look back at this Hamiltonian, if the Hamiltonian operates on the vacuum state doesn't have 0 energy, right? It has energy, in our case, equal to 1/2 omega, right? So the energy of the ground state is not 0, it's 1/2 omega, okay? And that'll come back when we go back to the field case. That's going to be an important So in field theory, we call it the 0-point energy or the vacuum energy, but we'll get to that, okay? All right, so we've defined the ground state, and then we build up our higher states, our higher level states, by using the A dagger, right? And we postulate that when we apply a dagger n times on the vacuum state, we get the nth state, right? That's something that we postulated, and we didn't derive. We just said, okay, let's try to use this, right? And then we worked out what the normalization factor is, right? That we've all done before, okay? So like I said, so this A dagger we defined to be something called the number operator, right? So it counts the quanta in that state, right? So when it hits the nth state, these guys are defined to be eigenstates of this n operator, and it returns back the eigenvalue n, right? The excitation number. Okay, so that was a quick review of how we quantize the quantum mechanical simple harmonic oscillator. Okay, so what we want to do is we want to use the same type of formalism, but for our fields, because what we've seen is the equation of motion, the Klein-Gordon equation of motion, gives us something that looks like the simple harmonic oscillator. All right, so we want to try to use that same type of formalism. Okay, so what we want to do is rewrite, like what we did before. We wrote Q and P in terms of A and A dagger. Here we're going to do the same thing, but we're going to rewrite phi and pi in terms of A's and A daggers. Okay, the difference is that these aren't discrete things anymore; they're fields, right? So they have annihilation and creation operators defined at each point in space-time. Okay, so that's where the complication comes from. So you don't just have, one set of A and A dagger. You have, if you were able to discretize space. So if you're watching this video later on, I'm drawing, what would you call this? Like a checkerboard, okay? And then at each point, at each crossing, is a point in space-time. And at each point in space-time, you have your own A and A dagger. Okay, in space-time, these guys would be labeled by x, the space-time point. Okay, so this is the space-time point. But we're working in momentum space, right? So we're going to label these guys not by x's, but by p's. Okay, and in fact, let's just forget about time for the time being. Forget time for the time being. Anyway, so so let's just label these states by the 3 momentum, or the three vector, okay? All right, so when we write down a field, we have to not only express it in terms of a dagger, right? But we're gonna have to integrate over all space-time, right? Or in this case, over all of momentum space, okay? And if we were working with the position fields, that we would just write in terms of a dagger, but we're doing we're working with Fourier transforms, right? So what we have are expressions that look like this, okay? So this is the analogy of x is equal to, some normalization constant times a plus a dagger, okay? Here, it's now a, the Fourier exponent times a dagger times the dagger of the exponent, okay? And we're integrating over all of momentum space. Okay? Sounds pretty complicated, right? But it's not. You'll get used to it. Okay? And these factors are thrown in just for to make the field Lorentz invariant. It's for Lorentz invariance reasons. Okay? I don't want to get into the details of that. Okay? So in general, you would write it like this. Okay? So you would write out the A and the A dagger, right? But a lot of times you can save yourself a lot of work by taking this P in here. So this P is just a dummy index. Okay, it's just being integrated over, right? And this is a symmetric integral. So what you can do is you can take the P in here to minus P, right? And it doesn't change anything, right? But what it does is if you take P to minus P, then you get a common exponent between these two terms, right? So you can pull out that exponent, okay? So that's what I've done going from left to right here in equation 20, right? And likewise, you can write down the momentum field in terms of A and A dagger. And if you go back and look at how we define the P operator for the harmonic oscillator, it looks a lot like that. And then I just do the same thing. On the second term, I take P to minus P, and it lets me pull out that exponent. Okay? Because in a lot of the problems, what you're going to do is you're going to take these fields and you're going to plug them into the Klein-Gordon equation of motion or the Klein-Gordon Hamiltonian, and you're going to want to work through it and work it out, right? And you don't want all these different exponents floating around because you're taking derivatives here and there, and it can get really confusing. So you can save yourself a lot of trouble by doing that trick, taking all the derivatives, and then in the end, take minus P back to P in those terms, okay? And we'll see probably examples of how that works, okay? But notice that the omega P, remember, it goes like P squared plus M squared, right? So it's invariant under this P to minus P little trick. Okay? So now we ask ourselves, okay, so we've got our operators, and we've got them written in terms of annihilation and creation operators. What kind of commutation relations does that imply for the annihilation and creation operators, right? And so you can plug those in, right? You can plug them in, or you can just go by analogy and say, well, we know what it is for the harmonic oscillator. They follow these simple rules, right? So let's just go to the continuous case, right? And the continuous case just changes these guys, these discrete guys, to continuous guys, right, that have subscripts now P and P prime, right? And because we're dealing with a continuous case, this Kronecker delta function becomes a three-dimensional Dirac delta function, okay? And as always, this factor of 2 pi cubed comes in for convenience, okay? It's something that you don't realize until after you do it, then you get, you work through the Hamiltonian or whatever, and you've got this stupid 2 pi cubed. And we all know that you can rescale the Hamiltonian by, constants. So you go back to the commutation relations and you throw in that 2 pi cubed there, and it cancels that off. So you don't, in the end, have to deal with it, okay? Anyways, all right? So you can take these relations and you can go backwards and actually show that, if I write the fields as I had them on the previous slide in terms of A and A dagger, and I try to compute this commutation relation using these guys, I get the canonical commutation relation between phi and pi. Okay? Make sense? So in the beginning, let me go back. So in the beginning, where is it? So going back to slide 3, right? Here, remember we said that we're defining our operators and we impose these canonical commutation relations, right? We postulate those, okay? So now what I'm saying is that in going from pi and phi, or phi and pi, to A and A dagger, right? You can use the commutation relations, these guys, to double check that you're doing things correctly. So you can go back and plug those field expressions for phi and pi, use these, and make sure that you get back the commutation relation that we postulate. Okay? There's a lot of homework problems on this, so I'm just kidding. I will submit. I will, you will have at least one. All right. What do we want to do now? Okay. All right. So we've got the fields, right? We know how to write the fields in terms of A and A dagger. We know the commutation relations, right? And so the next thing we want to do is we want to compute the spectrum, right? The spectrum, the energy spectrum for the Hamiltonian, just like we did for the harmonic oscillator, okay? And so we're going to do that, okay? So we want to ask ourselves, what does a Hamiltonian look like in terms of these annihilation and creation operators? So what I'm saying is we go back to equation 5, and in equation 5 we plug in equations 20 and 21, okay? So you see what I'm saying? I'm taking these expressions for phi and pi, and I'm going to plug them into that, equation 5. All right? Now when I do this, I have to be careful, because when I plug in, say, something like the term that goes like 5 squared, so I'm cherry picking the easiest term to show you how to do these, okay? You want to be careful, because those integrations that come in from the Fourier transform, remember, those are in terms of dummy variables, right? So they're being integrated over, right? So you want to be careful and don't use the same symbol for phi and for the two factors of phi, right? So this term's going like 5 squared. Okay, let me just take it in steps. So we have 1/2 m squared, right? Here's the d3x that's coming from here. And then I plug in equation 5 for this phi, okay? And there's two factors of it, right? So here's one factor of it, the d3p term, and then here's the other term, the d3p prime term, right? So I'm being careful with the labeling of p, okay? That's essential when you work out these things, okay? Because you can really, screw stuff up if you don't do that, all right? And the good thing is, we're going to see that if you do it correctly, delta functions will come and save your life. Okay, they'll make sure that you get everything right. Okay, so it's a lot like working with Lorentz indices. Be as general as possible, and delta functions will, they'll save you. Okay. All right. So this is what I have. So I put in my two expressions for phi. Right, then I can pull that p prime integral out. Okay. And now what I want to do is I want to use the x integration. I can use the x integration because why? Y, WHY, not Y, the letter Y, right? But here's the d3x, and the only thing that depends on x is the exponential, right? But that exponential, being integrated over d3x, is just the delta function, right? It's a delta function in p and p prime, okay? So you see the advantage already of using that trick of going from p to minus p, right? Because now I only have two exponents. It's giving me this one exponent when I combine them, and then I can use this Dirac delta function trick, okay? So that allows me to get rid of, once I do this integration, I get this delta function, that allows me to get rid of one of the p or the p prime integrations, okay? So I set p prime to minus p, right? And I end up with that, equation 25, which looks a lot nicer, okay? And now I can, what do? So I combine this stuff, right? And I make heavy use of the commutation relations. That means I'm moving stuff around, right, to get it in a particular form, because I know the form that I want, right? I know that from my days of studying the simple harmonic oscillator that I want one term that goes like a dagger, okay? And you can see now in going from 25 to 26 that I've made the replacement, in some of those terms, I've taken minus p back to p. Okay, I can do that freely now because that exponent's gone. Okay, makes sense? What I'm saying? Right, because the integration is symmetric, right, and p, so I can take p or minus p. All right? So I move some stuff around, okay? And I end up getting something that looks like this, okay? It's starting to look familiar, right? It's starting to look like the energy or the Hamiltonian for the harmonic oscillator when we use a dagger, right? The difference is we have a field, right? So we're integrating over all of space-time, okay? That's where the integral comes in, and that's where these the subscripts are reminding us, okay? But then you look at that and you say, okay, I know what that first term is. It's going to be my number operator. But what's the second term? All right, remember I said that anytime we write commutation relations like that, we're saying that that's at the same time. Right? And the commutator between a and a dagger from the same space point time is what? Yeah, it's a constant, right? It's just the delta function, right? Remember, let me go back and show you so you believe me, right? So you look at equation 23, right? Here's the general commutation relation between AP and a dagger p prime, But if P and P prime are the same thing, right, I get 2 pi cubed delta 3 of 0, right? And delta 3 of 0 is what? What's the delta function? It's 1, yeah, but I mean it goes to infinity, right? Right? It's an infinite contribution because this thing doesn't depend on P. Right? You can see that now this integral, when you integrate over this over all of space, you're going to get infinity. You're going to get an infinite contribution. Okay, so this is what I was calling the 0-point energy. So this is the vacuum energy. Okay, so this is actually the energy from nothing. Okay, right, and it just gets compounded from the fact. So this alone is infinity, right? But then when you compound the problem by integrating over all of space, okay? And so you get this infinite contribution to your Hamiltonian, to your total energy, right? And some people would say, oh, okay, well, we screwed up somewhere, right? Especially experimentalists would say, you guys don't know what the hell you're talking about, right? But then there's people that come along like Feynman, and Feynman was from Queens, okay? And Feynman was like, forget about it, you know, like the Sopranos, okay? He said, forget about it because why? Because you can't detect the energy from the vacuum, right? All you can detect are relative energies, right? So you have a ground state and you can detect the energy with respect to the ground state, but you can't detect the energy of the vacuum, right? So it goes back to that problem that we talked about when we were talking about the Dirac equation, right? Remember, he had the same type of problem where he had this infinite energy contribution. And he said, well, and he proposed that Dirac C, that all the electron, levels were filled, and that's why you didn't see these. And so that's the same type of idea, okay? So you just say, you know what, I know what the theory says, and yeah, it should be there, but we can't detect it, so who gives a shit? Okay? To paraphrase, fine. Okay? All right? Okay? So we don't worry about it. And in fact, we'll spend a couple weeks talking about something called renormalization, where we'll get rid of that term, right, by hand. Okay? And so we'll start with a Lagrangian, and we'll write down the normal free Lagrangian like this, but we're completely free to write down a term, a constant energy shift, right? It doesn't change the equations of motion at all, okay? But what we can do is we can put that term in, and when we compute the Hamiltonian, we get this, okay? So we get a normal energy term, so this is the normal number, so I'm looking at equation 28. So A dagger A is a number operator, and it's being multiplied by the energy. So it's summing up the energy of all the different modes, right? And then I get this contribution where this funny E times V was what we were calling our infinite energy on that previous slide. But this omega naught that I've added to the Lagrangian, I'm free to choose that. It's a free parameter, right? So I can just dial it to cancel off that total energy, to cancel off that infinite energy, okay? All right? So it works. It's an effective theory, okay? What it's saying is that we understand the theory up to some energy level, right? Beyond that energy level, we don't have a effing clue, right? But we do know how we can cancel that off, right? We can put in this extra term by hand, and we can cancel off those infinities, and we can still make good predictions in the energy range that we can measure, okay? So that's the basic idea of renormalization, okay? And this is kind of the bifurcation point in quantum field theory where, everybody's, happy-go-lucky until we hit the point of renormalization. And then there's a bifurcation. So there's a splitting of the road, right? And people either take the right path or they take the dark side, right? And so if they take the right path, they become theorists, right? And you say, oh, well, there's some higher level theory that we'll get to one of these days and we'll figure it out. Or you say, this is bullshit and I'm going to be an experimentalist, okay? Right? So, and I don't, you know, there have been people that I've taught that have, you know, actually done, you know, they don't buy it. And I don't blame you. It's kind of crazy, huh? Yeah. Yeah, exactly. I mean, what's, you know, I don't know. It's to me, it's perfectly fine, right? If you know, as long as you say, I understand that the theory is breaking down, right? I understand that, you know, at some high energy level, this is giving me garbage, right? Because it's giving me this infinite energy contribution. But if I can write down the theory and I can say, you know, let me just cancel that off and see what I get and compare it to experiment. And if it compares to experiment and it's right, then either, you know, both theorists and experimentalists are right or we're both wrong. You know, and usually not. One of us is usually wrong. Okay, it's usually experimentalists. But anyways, but there's all kinds of examples of this popping up. Okay, and so these are called because they're high energy types of divergences. They're usually called ultraviolet divergences. And there's two very good examples, okay? One is the Higgs boson, okay, the Higgs boson mass, okay? And we'll get to this, okay? So you might have heard about this. It's called the large hierarchy problem, right? And so what you find is that if you take the Higgs boson and you try to compute corrections to its mass, okay? So we'll learn about loop corrections, virtual type corrections, right? And if you calculate those, you get infinite energy terms, right? Or you get really high energy terms. And you have to cancel those off because you want the Higgs mass to be about 120 GeV, which is about 120 times heavier than the proton, okay? And so in order to do that with the standard model, you have to tune that omega naught, that counter, what we would call a counter term. You have to tune it by, you know, I don't remember how many orders, but you have to tune it so that you get two big numbers that are on the order of 10 to the 16 GeV, and those two cancel off to give you something on the order of 10 to the 2 GeV.
There's only 125 or so difference.
Yeah. So that's why it's called the hierarchy problem. Sometimes it's called the fine-tuning problem because you have to fine-tune this omega naught to get such a small number, right? And if you think we have it bad as particle physicists, there's a thing called the cosmological constant problem, where when you calculate the vacuum energy of empty space when you try to calculate the cosmological constant, you find out that you're off by 120 orders of magnitude. Okay, so you know you think particle physics has it bad, cosmologists have it even worse. Okay, but they can argue the same thing, right? And there are, you know, people have argued. Let me just throw out another buzzword before we take our halftime. So another buzzword is naturalness, okay? And people question whether or not this is natural, right? Whether this type of fine tuning, you know, where you have these constants that cancel off huge numbers, if that's natural, right? Would you expect that of a you know, some type of beautiful theory, right? And then the one counter example that people throw out is, and it's kind of stupid, but it's true, the size of the sun and the moon from our perspective, right? You know, these are two very different objects, right? But from our perspective, that's what gives us, you know, solar eclipses, right? And that's a perfect example of fine tuning in nature, right? Because I mean, what says that the angular size of the sun and the moon are going to be so close that, you know, you have this complete cancellation?
They're clearly not on, say, like Mars. It's got like those two tiny moons that wouldn't even come close to covering up the sun even from further away.
Right. So it's a perfect example of, you know, fine tuning in nature. Okay. So there's nothing horrible or, you know, evil about fine tuning. It can happen in nature. People still want to say that, you know, there's something that we're missing, right? There's some higher level theory that we're going to stumble upon, and it's going to solve all these problems. We're not going to have to worry about this, okay? Yeah.
I have a question. So for the Higgs boson mass, the 125 GeV, is it the theory come up with it first, or
No, you can't. No, you can't predict the Higgs boson mass in the Standard Model.
so it's basically because the experimentally find the mass of it, and then the theories can say that okay, then I will fine tune the omega naught to some number to get
Right.
to the mass.
Yeah, because the idea was that, you know, if the mass was more natural, if it was higher, if it was like in the TeV range, then it would make contributions to things that we measured before, like the Z boson mass, right? If it was really heavy, then its effects on the Z boson mass would have made the Z boson either lighter or heavier. I can't remember, right? But so they used arguments to narrow down the mass range of the Higgs, and they said, well, it's got to be somewhere between 100 and 200 GeV. I mean, that's all that's left, right? And that's where it turned out to be.
But isn't that in that case, it could either be the whole theory is wrong, or
No, we don't. I'm just kidding. No, up to that point, the Standard Model was, I mean, pristine. You know, there's only a few, you know, problems, okay, with the Standard Model. But everything that dealt with what we call the electroweak sector, like, you know, electromagnetic interactions, weak interactions, that had been tested out the wazoo, right? And we had tested it to so many decimal points. Everything was working perfectly, right? The only thing that was missing was how do the W and the Z get masses, right? They've got 80, 90 times the mass of the proton, and you're like, well, where does that come from, right? And one of the simplest ways to explain it was the Higgs mechanism, okay? Well, we'll talk about that more, because it's, you know, when the first time I taught this class, the Higgs hadn't been discovered, you know, so it was still, you know, whatever, theoretical or hypothetical. But now we know that there's a Higgs, and it's, you know, what mass it is, and so we can talk more concretely about, you know, the electroweak sector, okay? But we'll do that more later on. All right, so let's take halftime of about 5 minutes, and then we'll come back and talk some more about canonical quantization, all right?
My cousin actually teaches kindergarten and stuff. Yeah, so she's pretty good with younger kids.
Yeah, I don't know how they do it. It's really hard. Because they just get, you know, a lot of times it's not them being bad, it's just they get excited, you know, and they start talking about everything, about their camping trip, and, you know, when they saw a supernova go off, and, you know, it's crazy stuff, you know, and you're just like, yeah, okay, cool, man, that's great, you know, because you don't want to squash their, you know, their enthusiasm and tell them, no, you didn't see it. Crazy, you know.
Dumbass.
Yeah, exactly. You know, but, so it's a struggle.
What'd you build?
Well, today we built, so we were trying to teach them that, because most of them think, you know, that constellations are
Close to each other.
yeah, all the stars are right next to each other and they form these cool little shapes. And so we built like a three-dimensional model of Orion, right? Because the stars in Orion you know, are like thousands of light years apart. So I think some of them got it, but a lot of them are, really smart. I mean, the kids that age, a lot of them get obsessed with stuff, and so these are kids that got obsessed with astronomy, and so they know like every minute detail.
Sounds like me at that age.
I think it's this way.
Yeah. So like, for example, today some kid threw out the term plonk time. It's like you're a little ahead of the class.
Wow.
Yeah.
Even he doesn't know.
It's just, yeah. But I mean, they just throw, this kid is, it's amazing, really. Like my son, when he was like 4 or 5, he got obsessed with dinosaurs, so he could tell you like every
Also
single
sounds
detail,
like me.
Yeah, about every dinosaur you could ever think of.
I'm proud out to him that I still can do that.
Yeah. See, but he's forgotten a lot of it, there's been different times, that he got obsessed with that. He got obsessed with like the Old West, so he could tell you anything about, the late 1800s, of west of the Mississippi. He could tell you anything that happened. But now he's forgotten it, and he's moved on to other stuff.
What TCC campus is it?
Is that Northwest? Yeah. But I don't know if they do it at all the campuses or not. But it's college for kids, so they.
Yeah, I used to work at the Northwest, and they always had something, but
Okay.
I would say it's the one in the South.
Okay. Yeah. Yeah. So it's cool. They go to classes for 50 minutes, and then
Yeah.
I just have to watch. I have to watch what I say, and I want to make jokes. They won't get it, But yeah. yeah. That would, they just wouldn't understand. Let me try to remind myself what we're gonna do here. Okay. Yeah. Okay. All right. Now I remember. All right. Took me for a minute. Okay. So what I want to do now is go back and try to solve the problem again. Okay. But solve it in a slightly different form. Okay. So I'm going to start with the classical Lagrangian. I'm going to solve it classically. Okay. It's going to be, and then we'll quantize it. Okay. So instead of quantizing the fields right off the bat, we're going to try to solve the equation of motion and then work with those solutions, okay? And we'll quantize those solutions, all right? So let's start. We'll start with the classical Lagrangian that we had before, right? And we know that when we apply the Euler-Lagrange equations of motion, we get nice little compact equations of motion, right? That in momentum or in position space kind of look like wave equations, right? And so we know that they're wave equations, so we know what the form of the solution is. It's just a plane wave. Okay, so remember, we're in classical mechanics here. Okay, so our wave looks something like this, where the plus or minus means we're either propagating to the left or the right. I can never remember which. Okay. All right, and again, omega is just going to be square root of the wave vector squared plus the mass term squared. Okay, but remember, it's not technically a mass term yet. Just some parameter. Okay. And so just like we saw before, if we want to solve this thing, it's to our advantage if we work in momentum space, okay? And so what I want to do is write out a general Fourier transform for the field phi, okay? Now, when I do that on equation 29, okay, what I'm doing is I'm writing out a general classical Fourier transform, okay? So I'm writing this field in terms of left and right going waves, right? You see the two exponential terms, right? I'm integrating over K because it's a Fourier transform. But A and B here, don't get A and B confused with A and a dagger yet. Okay? All right, so they're just general coefficients at this point. Okay? And what? Oh, we've assumed some boundary conditions and blah blah blah. Okay, normal classical mechanics type stuff. Okay, and we've also included for convenience, right? This redundant function of k, which we're going to call f of k, right? And we've already seen. I just kind of threw it in by hand earlier. It was that square root of 2 omega or whatever, right? It comes in. We'll see it comes in because of, or we need it because of Lorentz invariance. Okay, because we want to work with relativistic fields. Okay, so we'll determine that in a little bit. All right, so we've got our field, and remember we're working with a real Klein-Gordon field, so we want phi star to be equal to phi. All right, so if I write down phi star, I would have something like this. Okay, and then what I do, I want to take, because I want to compare this to the real field, so I take in the second term, again, I use that trick where I take k to minus k. Okay. So I'm assuming that this thing is quadratic in K, it's symmetric in K. Right? So I do that, and if I compare those two expressions, then I can make a relationship between B star as with argument of minus K being equal to A, right? Because if I compare the exponential terms, right, I see that this guy is equal to that because I want the field to be real. Right? And likewise, I find that B is equal to A star with a minus K. Okay? So what does that do? So it lets me eliminate B, basically, right, from my solution for phi. Right? So I've replaced B with A star minus K. Okay? And going from equation 29, I'm taking B and I'm replacing it with A star minus K. Okay? It's star, not dagger, because remember, we're in classical mechanics still. Okay? All right. So what do I do next? So it looks like I take K to minus K in the second line there in the second term, right? And then I use our 4-vector notation. Okay, so here I have minus K dot x plus omega t. Okay, so this is something I should have pointed out earlier, and this is where the confusion will set in, is that this discussion is following the discussion in Srednicki. Okay, and in Srednicki, they use the, what metric? West Coast metric, right? They use the wacky metric, okay? So there will be, if you go back and you look at these notes, and you compare some of the expressions before with the expressions here, you're going to see some minus sign differences. Okay, in the end, the physics will be the same. It's just in the intermediate steps there's going to be some differences. Okay, and one of those differences is the definition of a dot product between two 4 vectors. Okay. All right. Even though that looks like, isn't that Okay, hold on. See, now I've already gotten confused. Okay, so Kx, if I'm using oh, is it because x is down, k is up? Yeah, I think it's because, no, that can't be right. I don't know. Let me think about it. It'll come back to me. Okay. But the point is that we're using a different metric here. Okay. And okay, now it's okay. So I think what I've done is I started out by saying that Srednicki works in the West Coast metric, but then I made the conversion back to the East Coast metric because I hate the West Coast metric. Okay? So forget about that stuff that I said about difference in minus signs, because this is what we would get in the East Coast metric. Right? Remember, time is the 0 component. of the position 4 vector, okay? And K is like, it's like the energy, or the momentum 4 vector, okay? So that's what we would get, okay? And that means that if I take K squared, right, and I take K dot K, so this would be omega squared minus the linear momentum squared. And omega squared is just the energy squared, right? So that's this, okay? And these K squareds cancel off, and I get this factor of plus M squared, okay? And anytime a 4 vector obeys that relationship where you have K squared equals M squared, where M is now the mass, that vector, that forward momentum is said to be on mass shell, okay? We'll come back to that. It's just, I'll probably say that, so I wanted you to know what it meant, okay? If you're working in the West Coast metric, if you look in Srednicki, you see this expression K squared, it's going to be minus M squared, okay? And that's why I say that's why the West Coast metric is just crazy, okay? Because who has a mass shell relationship that should be positive energy and it's minus M squared? It doesn't make sense, okay? All right, so this is East Coast metric, okay? So we gotten it down to this point, right? And what we want to do next is figure out what this f of k is, okay? I don't want to go through the details, but you basically just enforce Lorentz invariance, right? Invariance under Lorentz transformations. And so you can write down a Lorentz invariant measure, okay? So the measure of the integral, so the integral over the space and some delta function and some step function to ensure that you have positive energies. And you go through some tricks, and sure enough, you find out that this f of k is that factor of 2 omega, right? In fact, you get a square root, okay? So you can work through this on your own. I don't want to waste time on it because all it does is confuse people, okay? All right? So Srednicki does, the one thing he does that I do like is he introduces some shorthand notation, okay? So he introduces this shorthand notation for the integral measure because you always get these factors 2 pi and this 2 omega that come along for the ride with this d3k. And so what he invents this notation, I've never seen it before, with this dk squiggle, the dk twiddle. And he calls it d-lips, which always makes me laugh, but it's, so here, if you look in his book, you'll see integrals over d-lips, like this, okay? And d-lips is Lorentz invariant phase space, okay? And that's what that is, okay? So if you look in his book, like I said, you'll see d-lips in there, and that's what it means, Lorentz invariant phase space, okay? So we went through, we wrote down the solution for the field. We said we wanted it to be Lorentz invariant. The way we enforced that was through those the normalization, right? And we knew how to, from our days of, special relativity, we knew how to write down a Lorentz invariant measure. And from there, we were able to deduce what this f of k function was. In any case, all right? So we get our nice, compact solution for the field, right? This is the classical field, okay? What do I do? Oh, so one thing that's sometimes useful is you can take this expression and, like, remember when we talked about the simple harmonic oscillator and we defined, what do we define first? We define A and A dagger, right? In terms of, I can't remember the constants, but it's x plus IP or something like this, x minus IP. Right, and then you go through the exercise where you invert them, right? So you write x in terms of A and A dagger, and p in terms of p in terms of A and A dagger. You can do the same thing in this type of formalism, right? So I can take that field expression, I can do a Fourier transform on it, right? And then I can do the same thing for the pi field, and I can solve for expressions for A and A dagger, okay? So this, again, is going through some algebra that I don't want to bother with. The only thing I do want to mention is that sometimes you'll see this notation here. Okay, so this is an equation 44, right? So here we've inverted phi and phi dagger, or phi and phi dagger, phi star in terms of A star, okay? What I have is this kind of derivative that has double points on it, okay? And it's shorthand notation for this, equation 43, okay? So it means that anytime you see this, it means this, okay? It's just a way of shortening up your expression, okay? We don't work that much with A and A daggers, the field expressions, so that's why I'm not wasting much time in covering, this derivation, okay? But it should all be there. If you have questions about it, let me know, okay? But like I said, it's not that useful, okay? All right, so now we've got the expressions for the fields. We can take, we know how to get the expressions for the conjugate momenta, right? So we can construct the Hamiltonian, right? Still, we're in classical physics, okay? So I can take the equations that we worked out last week for the Hamiltonian and the conjugate momentum, right? And I can work out what the Hamiltonian is in terms of A and A star, okay? Note that from the beginning, I kind of know already from our earlier discussions that I'm going to run into some infinite energy problems. So I'm going to go ahead and put in an extra term into my Hamiltonian, okay? I'm free to do that because this is a constant, so it's not going to change the relative energy levels, okay? But it is going to save me in the end. Okay, so I can write down the Hamiltonian. I can replace anywhere where I have pi, I can replace it with phi dagger if I want, or phi dot if I want to, right? And in the end, if I multiply all this stuff out, and I keep in mind that in the end I want to quantize this theory, right? So even though A and A star are just classical objects, classical vectors that can pass, or functions that can pass through each other, I'm going to keep the order straight because I know I'm going to quantize this, okay? So if I keep everything straight, I end up getting something that looks like this in equation 46, okay? So this is what I would get for a classical Hamiltonian, okay? All right. But classical fields are boring, so let's go to quantum fields, okay? So quantum fields, I know that I've taken my Hamiltonian. I know what my operators are. They're phi and pi, right? And I can derive, so what I'm doing is I'm taking pi and phi, the field and the momentum field, promoting them to operators, right? That means that when I look back at the expression for phi, where is it? So when I promote equation 40 to an operator, these exponents are just numbers, right? They're being integrated over. That means that these guys are going to become operators, right? My coefficients, A and A star, okay? So they become A and A dagger, right? So that means that when I impose the normal commutation relations on phi and pi, they become commutation relations on A and A dagger. They end up being the same commutation relations that we wrote down before, okay? So all I'm doing, I'm just doing things differently than what I did before halftime, okay? I'm just going through the solution all the way classically and then promoting everything, okay? And so what I get from the Hamiltonian is something like this when I move some stuff around, okay? And you can see I get, again, this commutation relation between A and A dagger for the same K, right? And that's going to be the piece that gives me that delta 3 of 0, right, the infinite piece, okay? And you can see it, it's right here. And so what I do is I define this guy to be this epsilon naught. And then in the end, I can tune the omega naught, the counter term, that term that we put in by hand, I can tune it to kill off as much of that epsilon or that E0 as I want, okay? V here is just the volume, okay? That's what makes it infinite because it's the volume of all of momentum space, which is infinite, okay? All right, and so again, we see the appearance of this vacuum energy, right? The vacuum energy being this E naught, okay? And it's coming from, like I said, summing all of the constant energy terms, right, that we would get in the simple harmonic oscillator case for all these points in momentum space, okay, for all the oscillators. And if we integrate over k, we see that it's indeed infinite, right? But how do we cut it off? Like, so before I just, kind of waved my hand and said, we can put this term in, we can cancel off the divergence, right? But what form does the divergence take, right? And to answer that, the way you can do it is you can put in a cutoff, right? So you're integrating over momentum, okay? From 0, you integrate out the angular stuff. It just kills off some of the 2 pi's, right? But you're left with this momentum integral, right? It goes like dk k squared, and there's an extra k coming from somewhere in here. I can't remember. Here, so here's a k squared, and there is, I have to remember where the extra, I'll think, is it from omega? No. Omega. I think it is. I think it's because we are, so what I'm doing here, so here everything's good, right? And I'm writing out the d3k integral in terms of the angular components, and then the dk k squared, right? But inside omega, I'm taking the large k limit. All right, so omega, remember, is k squared plus m squared. All right, and what I'm saying is that the divergent behavior of this vacuum energy is going to come from large values of k. So I'm replacing omega with k. Okay, I'm neglecting that mass term because it's small. Okay, so that's where I get this k cubed term. Okay, so you want to do that integral, right? But that integral is from, in theory, it's from 0 to infinity, right? It's over all of space. But you're saying, okay, I'll be humble, right? Maybe I can't explain, theory of at all energies, right? So let me cut it off. Let me put in a momentum cutoff, okay? So what I'm saying is that, I have this picture where, I live down here, okay? So here's, let's say this is, what's a good energy range? So this is like the mass of the proton, okay? And this is the energy range that we typically live in, right? So here's Lem. Here's a picture of Lem. He's happy because he's living in the energy range that we live in, right? But up here, there's some energy range that I don't know what the hell's going on, okay? But I know that the standard model or whatever theory I have can explain this energy range just fine, right? It's this stuff up here that I don't know about, okay? And this stuff, so this is this is the energy range here. I can say, okay, at some cutoff, at some region in the energy range, I don't know what's going on. Okay, so let me just integrate up into that point, and I'll cut it off. Okay, so this is a way to kind of quantify, our ignorance really of what lies above in the energy range. Okay, so that's what I do. I replace the infinity that would be here with some cutoff lambda. Okay, and then I say, okay, that integral I can do, right? It's just k to the 4th over 4, right? And then I put in the limits. Okay, so I get something, this vacuum energy that goes like lambda to the 4th. Okay, and then you say, okay, what's a good value for lambda? Right? What do I use for lambda? Right? Is it, all we've really probed up until this time is like, something on the order of 1 TeV. This is like 1,000 GeV, right? So really, is our theory only good up to TeV range? Probably not. It's probably good to a few TeV, maybe even higher, right? So some people say, well, this is like, they call it the gut scale. It's on the order of 10 to the 15 GeV. Anybody know what gut means?
Grand unified theory.
Right, grand unified theories, okay? So these are theories where you unify all the forces, okay? And they typically unify in an energy range of 10 to the 15 GeV, okay? So this is what is called grand unified theory. So you'll hear that term a lot, gut. Okay? So a gut theory might say, oh, the lambda is on the order of 10 to the 15 GeV, right? And if that's the case, that's when you need these large cancellations, right, in order to get, say, a Higgs mass of 125 GeV, right? Okay? So that's just a way. So before I was just saying, you know, we were going to get an infinite term. Let's cancel it off right from the beginning. But here you can kind of quantify, like I said, our ignorance of, you know, what lies above, right? How far off are we, you know? Okay. Right. And so one way of saying this is that, you know, this is the contribution from the stuff that lies above, right? Because if we have a good theory, then we're not going to have infinities, right? So if we don't have infinities, that means that the stuff that lies up here, right, whether it be supersymmetry or, you know, what other weird theories there are, extra dimensional theories, there's going to be contributions from those fields that live up there. They're going to cancel off this guy, okay? And that's how you kind of argue the existence of this thing, okay? You just say, well, we're stupid right now. We don't know how to explain the whole energy range, but it's, you know, we you know, so that they would argue that this theory is what they call UV complete. There's a lot of cool buzz terms in high energy physics. That's why you should become a high energy physicist, man. All right. What else? I think that's it. Yeah, that's it. Ah, okay, so we finished early. Awesome. All right, so what I'll do is, well, I'll just stop there because that's a good breaking off point. Okay, and then before we go, let me see what we'll talk about next so I can tell you. You guys want me to go over? I can go over my astronomy. What is astronomy? And you guys can yell out what astronomy is. Let's see. What do we talk about next? Got too many talks in here. Answer is I don't know what we're talking about next. I'll figure it out before next time. Okay? Huh? Yeah. Thursday at 3:30 I'll figure it out. And I'll let you know. Okay? But we'll go ahead and call it quits today. And like I said, I'll put the link to this. I'll put the slides and a link to the YouTube. Yeah. It's already there. I know what it is. I just don't know what it is. Okay? So keep this picture of Lem in mind. All right? Living down at the energy range. Right? And remember D-Lips. Okay? So go look at Sir Nicky and you can see how he works through this stuff in a different way than what I presented in the first half. Okay? But if you have questions about anything, email me, okay? And I'll ask that kid in my astronomy class and have him get back to you, okay? All right. I'll see you guys, what is today, Tuesday? I'll see you Thursday.